Hello YouTube. In my last two videos I translated the Lagrangian formulation into the Hamiltonian picture, and then we looked at a special type of coordinate transformation among the Hamiltonian phase space coordinates called the canonical transformations. Let's look at a special case of an infinitesimal canonical transform, which is a coordinate transformation that effectively adds dg dp to q and subtracts dg dq from p. If k is small, then big Q and P almost equal little q and p respectively. And this approximation is where you can substitute little p instead of big P, and in the limit where k tends towards 0, that approximation becomes exact. Sometimes G generates a Hamiltonian symmetry. This means that the change in H as we modify Q and P by this amount shrinks to 0 for small k. To clarify, this means that dH dk equals 0 at k equals 0. But if you expand out the dependencies on k, this statement implies that the Poisson bracket vanishes and G is a conserved charge. Consider the special case where G equals epsilon p. The system will preserve epsilon p if, adding epsilon to q and taking p d epsilon dq away from p, leaves the Hamiltonian unchanged for small k. Is this observation equivalent to the Noether theorem I introduced earlier? Remember, Noether's theorem assumes that there exists epsilon such that there's no change in Lagrangian when q changes by epsilon and q dot changes by epsilon dot. If such an epsilon exists, then does it imply that there is no change in Hamiltonian when we vary q by epsilon and vary p by this much? Well, it does as long as the Euler-Lagrange and Hamiltonian equations hold. This means that q dot equals dH dp, dH dq equals negative p dot, which by Euler-Lagrange equals negative dl dq. P is, by definition, dl dq dot. We can assume that they hold because the Noether theorem is predicated on the equations of motion. In the old statement of Noether's theorem, the Lagrangian statement, the change in q dot is obviously the derivative of the change in q, which is epsilon. It's not so clear that the change in momentum here is consistent with epsilon in this way. Is it consistent? Well, q dot is dH dp, so the change in q dot is actually the Poisson bracket between dH dp and the generator G. By contrast, the time derivative of this quantity, the change in q, is the Poisson bracket between dg dp with the Hamiltonian. So the special case where G is a Hamiltonian symmetry, say epsilon p, implies that the Poisson bracket vanishes, so its derivative vanishes, and the implied change in q dot is indeed compatible with epsilon dot. Now, thus far in my video series I've considered the autonomous case in the Hamiltonian picture. But the Hamiltonian and Lagrangian are related by the Legendre transformation, so in the general case the Lagrangian and Hamiltonian can show explicit time dependence. Now, if we wanted to get around this, there's a little trick. Suppose I define a new coordinate, tau, and its conjugate momentum, which is e. So I'm going to replace t with tau everywhere I see, and define a new system where big H equals our old Hamiltonian minus e, where e is a momentum coordinate. What are the Hamiltonian equations of motion? Well, q dot is dH dp, and p dot is negative dH dq, except these functions now depend on tau, our new system coordinate, instead of time. But how does tau evolve? Tau dot equals dH dE, which is just 1. So what about E dot? The time derivative of E is dH d tau, which is the partial time derivative of our old Hamiltonian, except with tau in the place of time. Okay, so now we've constructed a system that does everything that our old one does, except it's autonomous, because the Hamiltonian is free of explicit time dependency. It doesn't involve t anymore, it involves tau. In some sense, our new coordinate, tau, serves as an internal clock. Meanwhile, the conjugate momentum for time measures the change in energy that our old system would have undergone. If we can reformulate our system autonomously in the Hamiltonian picture, can we go backward to form a time-independent Lagrangian? Well, not quite, because to Legendre this Hamiltonian back to the Lagrangian, we'd need to solve for velocities in terms of momenta, but the velocity for tau equals 1, so the coordinate transformation is degenerate. But we can do something that's almost as good. What if we recast q's and p's as independent coordinates with their own conjugate momenta? So we reverse engineer the Lagrangian as q dot p plus tau dot e minus h. So no need to solve for p in terms of q dot, because p is now a coordinate on level footing with q. We can verify that the Euler-Lagrange equations for this system are exactly the Hamiltonian equations. dl dq, which is negative dh dq, equals the time derivative of dl dq dot, which is p. On the other hand, dl dp dot equals 0, so the conjugate momentum to p is 0, and hence dl dp, which is q dot minus dh dp, must equal 0. This is called the secondary Lagrangian formulation, where the canonical momentum, the conjugate momentum to q, equals p, which is itself a position coordinate. The conjugate momentum for p equals 0. Well, that saves us from dealing with time-dependent Hamiltonians. As you expect, a time-dependent Hamiltonian is the Legendre transformation of a time-dependent Lagrangian, and we still define p as dl dq dot. Okay, so the evolution equations of q and p stay the same in the time-dependent case, and so the basic equations in the time-dependent case also stay the same. Okay, if you have a time-dependent quantity, for example a, which is a function of phase space coordinates, and also t, then its time derivative is this Poisson bracket plus partial dA dt. Suppose you have a whole bunch of quantities labeled q1 to qn, and another n quantities labeled p1 to pn, and they're canonical in the way that I described in my last video for every value of t from 0 to some future time. This means that the Poisson bracket between qi and pi equals 1 for I ranging from 1 to n, while all other pairs have 0 Poisson bracket. We can generate a canonical transform from any arbitrary generating function, and if f varies with time, then the canonical transformation is also dynamical. But what is the evolution rule for q1 or q2? In the static case, we saw that q dot is just the Poisson bracket between q and h, but now there is time dependency, we need to add on this partial derivative. Likewise, p dot equals the ph bracket plus partial dp dt. I want to express these partial derivatives in terms of the generating function f. Okay, well, the definition of big and small p in terms of big and small q gives us derivatives holding the other q constant. But we want to differentiate big q and p holding little q and p constant, and to do that we rearrange the matrices like we did last time. And just like before, we call these A, B, C, and D, where the change in big Q in terms of little p and little q now has this extra term for time dependency, and the change in big P gains this time-dependent term. By definition, this is the partial dq dt holding little q and p constant, and likewise this is partial dp dt. Well, guess what? Partial dq dt actually equals the Poisson bracket between q and partial df dt. A direct calculation gives these terms, and these two cancel, so we end up with this, which by comparison is exactly what we found earlier. Similarly, we can do a direct comparison between our matrix expression here and this Poisson bracket. So the moral of the story is that a time-dependent canonical transformation, big Q and P, evolved by H plus partial df dt. Now, is there a simpler and more concise argument? Okay, well, let's just suppose that delta t separates these two stationary time points. The coordinates at a later time point, big Q and P, are some canonical transformation of the little q and p, but as delta t shrinks to 0, the transformation becomes infinitesimal. In the infinitesimal limit, this time increment adds on dg dp and negative dg dq times delta t. Holding little q and p constant, these are our partial derivatives. Substituting, we see that the total time derivative of big Q and P really is the Poisson bracket with h plus g. But g, the infinitesimal generator, is the increment to the generating function from one time point to the next instant. So in other words, g is df dt. Time-dependent canonical transformations open the door to Hamilton-Jacobi theory. Suppose we found some canonical transformation that caused all of the new variables, big Q and P, to remain stationary. So this means that we express the Hamiltonian in the same variables as f, h plus df dt equals 0. This is called the Hamilton-Jacobi equation, and the Hamiltonian equations in the new coordinates become trivial because the time derivative of each of the big Q and P are going to be 0. In other words, they're going to be set by the initial system state as constants of motion expressed in terms of the original little q and p, and possibly time. For example, df dp equals big Q in terms of little q and big P, but big Q and P are constants we solve from the initial conditions, so we really just have little q as an implicit function of time. Hamilton-Jacobi theory shifts the work of solving Hamiltonian equations to solving this partial differential equation, the Hamilton-Jacobi equation. The two problems are actually equivalent, so it's just a matter of preference. When the variables obey all equations of motion, df dt is surprisingly equal to the system Lagrangian. Why do I say that? Well, its total time derivative of f partly depends on how quickly q and p are changing. We know p dot equals 0, and the Hamilton-Jacobi equation holds, and the coordinate transformation defines little p as df d little q. So this becomes p times q dot minus h. Well, that's just the classical Lagrangian, and so the value of f is equal to the time integral of the classical Lagrangian. In other words, f is actually equal to the classical action. Alright, I'll see you in the next video.